Welcome back, ladies and gentlemen. In this video, we're going to apply the skills from the previous video about graphing to constant motion, an object moving at a constant velocity. So remember Mrs. Kangaroo and Junior. So we'll get to her and her situation in a moment. So why do this? Why graph this data that we record for a moving object? Well, there's a lot of knowledge in one graph. And we're only going to look at one graph today, but we're going to see more examples and more sophisticated situations. And these graphing skills are extremely important. Also, when we graph this data, we are able to create a bridge between what we observe in the situation and mathematical equations. And this to me is where the physics really starts to get interesting, where you understand where some of this stuff comes from, like some of the equations that we use in physics. These equations don't just appear out of nowhere. Scientists don't imagine them or dream them up and then say, oh, well, they seem to work, so we're going to keep using them. Well, actually, no, not at all. The equations, the mathematical relationships, they come about because they exist in nature already. No, the equations and the symbols don't exist in nature, but the relationships between things do. And it really is a mathematical, well, maybe I shouldn't say a mathematical universe, although you could, but it can be very accurately described using mathematics. And it's not complicated math. You'll see. So our situation is Mrs. Kangaroo is moving, and we're tracking her position every second. She's on each dot 1 second by 1 second, and she's traveling 2 meters each time. You can see the consistent spacing between the dots, and she's traveling in the positive direction indicated by our coordinate system that we've drawn, and that's really for our convenience. And we track the data. We have it organized here in this table. The time measured in seconds, we track for 5 seconds, and the position measured in meters, and it turns out, let's see, 2, 4, 6, 8, 10 meters of total distance traveled. Okay, so we're going to graph this data. I have, well, this is going to be interesting. Okay, so what is the dependent and independent variable? Well, it turns out if you say this both ways, so does the position depend on how much time has gone by, or does how much time has gone by depend on where Mrs. Kangaroo is? You'll sort of think, okay, and then one of these makes sense and one doesn't. So if 4 seconds have gone by, she's here, and so that her position depends on how much time goes by. But if you say it the other way, how much time goes by depends on her position, well, that means, well, if she goes back by 1 dot, by 2 meters backward, well, then time would go backward. And that simply doesn't happen. So we know that our dependent variable is actually the position, and our independent variable is the time. We're kind of watching what position she's at these various times. So our independent variable on the horizontal axis, dependent variable on the vertical axis here. The scales that we're using, we have from 0 to 5 seconds, so we have to go from 0 to 5 on the scale to encompass all of the data. The scale here for this vertical axis, we go from 0 to 10 because our data goes from 0 to 10. That's actually really easy. Okay, and so we plot the points. We do that as carefully as we can. We do a line of best fit. Excellent. So now what? Well, it's easy to see this linear increasing relationship. Okay, and whenever you see a linear relationship, you will always want to find the slope of that line. And so this should be a review for you. You find the slope of a line on a graph. You calculate rise divided by the run. And the rise is simply the change in the vertical part of the line, and the run is simply the change in the horizontal part of the line. So our rise, you remember what the delta x represents? Well, that's a change in position. That's a displacement. Okay, and our run is a change in the time. So displacement divided by time, well, that means the slope of this graph represents the average velocity. Whoa, so this is really cool. The graph came from actual just observation of a situation, but the graph, within the graph, we see the slope of the line represents a physical quantity that's important. average velocity. And so we have an equation here, and then we'll plug some data in. Remember delta x, that change in position, final minus initial position, 10 minus 0 meters, and time, final minus initial, so 5 minus 0. So 10 meters, divided by 5 seconds gives us 2 meters per second. That's the average velocity of Mrs. Kangaroo, 2 meters per second. Okay, but we have from the graph, we have an equation that's going to be really important to us. And I want you to remember this very, very well. We're going to call this the first equation of motion, and there are going to be several others. Average velocity is equal to displacement divided by time, or average velocity is equal to delta x divided by delta t. You can say that either way. Now, there's another way to express this, and you'll see this also. This can be rearranged because remember we can expand the delta x into final minus initial positions. The delta t, we typically don't expand that like this because almost always we're going to start our observation and start timing something with time of 0. So if you do that and you rearrange this, it's quite often helpful to rearrange this equation and solve for the final position, because quite often you'll know the other information. You'll know the initial position, you'll know how much time goes by, and you'll know the average velocity, and you'll want to find how far they end up, how far the object goes. And so this is just a different form of this same equation. These two are the same equation. Don't think that they're different. It's just a different look to it, a different form. That's all. So this is what we have to deal with when we are graphing constant motion. And when the motion is constant, well, okay, so that means the average velocity is constant. And since average velocity is the slope of the graph, the slope should be constant. The slope must be the same slope all the way up the graph. That is so important. Yes, we'll deal with the mathematics. Yes, you'll have to do some calculations. But remember, please, that for constant velocity, a position time graph, this is, you'll hear me call it a position time graph or a PT graph, the slope is constant. It's the same slope all the way up and down. That tells you constant motion on a position time graph. And that means the average velocity is the same for the entire time. Thank you for watching. I'll catch you next time.